Hey guys, welcome back to another video. In this video, we're going to learn about gravitational potential energy. Now, up till this point, we learned about how the force varies with different distances away from Earth and how the graph looks like inside Earth and outside Earth. And we saw that as you move away from the surface of Earth, the force per unit mass actually decreases. That means the gravitational force decreases with increasing distance. Now, in this video, what we're going to learn about is gravitational potential energy. You might have already studied this in O-level or previously. And in those cases, what we used to do is we used to consider the gravity to be constant, right? We used to consider gravity to be 9.81. And that is all right, considering you're taking the height, the change in height to be near the surface. That is, the change in height is very small compared to radius of Earth. And I talked about this in the previous video, where the change in height or the height is so small compared to the radius of Earth that it does not change the ultimate value of force. Which is why you can use this formula that you used to do for positions that are close to the surface of Earth, right? In those cases, it's not going to change your gravitational potential energy. Now, what we used to see is, let's say, this pen. I'm lifting this up to a distance of 1 meters. I am putting in energy into the pen. And what we used to get is, let's say, after lifting it by 1 meters, it gains, let's say, this 100 grams of mass, 0.1 kg, times gravity 9.81, times the height 1 meters. It's supposed to give you 0.98 joules of energy. What this tells you is the pen has gained 0.98 joules of energy as its potential energy. Now, that statement is actually correct, that it has indeed gained 0.98 joules of energy as it moved from this position to this. That is this is not 1 meter, but this, right? It has gained 0.98 joules of energy. That is absolutely correct. But if you frame the statement as the gravitational potential energy of this pen after being lifted by 1 meters is 0.98 joules, then the statement is wrong. Because gravitational potential energy is actually always negative. And that is an interesting thing that we're going to discover in this video. Why is it negative? And why is the statement that its gravitational potential energy is, let's say, 0.98 joules wrong? You are indeed putting in energy and giving it 0.98 joules of energy in the form of potential energy, but that is not its ultimate potential energy. You have provided that energy, but that is not its potential energy, the net potential energy. So, one by one, let's start from how we used to define gravitational potential energy. That is, we used to say gravitational potential energy is the energy of an object when it has been lifted off the ground through any distance. The amount of energy it will have relative to its height above Earth. So we used to say gravitational potential energy is mg till h. Again, considering g is constant, that means near the Earth's surface. Now, what this used to consider is near the surface or on the surface, the amount of work done or the amount of potential energy the object has is 0. And the moment you lift it up by 1 meters, it gains 0.98 joules. However, that is not really correct. I mean, it gains 0.98 joules, but at the surface, it doesn't have 0 joules of potential energy. It actually has a really large negative value of potential energy. Why does that happen? Let's see. Now, this is a way you can define gravitational potential energy in general, but this is not how you're going to write in the question paper. I'm going to show you what the real definition is. But you can say the gravitational potential energy is the energy an object possesses due to its position in the gravitational field. That is, let's say I have an object here, and relative to the position of this object, if it is near to the Earth's surface, it's going to have a specific potential energy. If it is farther away from the surface, or I mean from the center, sorry, I keep saying surface, not surface, center. If it is farther away from the center of Earth, that means it will have a different potential energy, right? Therefore, relative to its position, it's going to have different gravitational potential energy. Now, let's say from the surface of Earth, if you are lifting this object up, you're doing work on the object. You're putting in energy into the object for it to be lifted up by any change in distance. Now, the heavier the object, the greater amount of energy you need to do. So therefore, we know that we are increasing or putting in work into the pen to lift it up by a distance. Therefore, we're putting in energy. We are doing positive work done on the object. Now, what we used to consider is at the surface, the energy is zero. However, that is wrong. Why? Because notice, at infinity, at a distance that is at infinity, in that case, the amount of work done on the object is going to be zero. Its gravitational potential energy is going to be zero. Why is that the case? It's because at infinity, there is no gravitational field strength of the Earth. Because at infinity, the field lines of Earth are so far away that at the end of the day, no amount of force is exerted on an object that is infinitely away from Earth. So, at infinity, mind you, no amount of force is being exerted on the object. Therefore, the energy the object will possess is zero. The energy the object will possess at infinity is zero because no amount of force is being done on that object. However, at the surface, if you consider the energy to be zero, you cannot increase the value from 0 to 0. That is, you cannot do positive work done and transfer your own energy to the object and increase it to 0. That is not possible. So, granted, we understand that at infinity, the gravitational potential energy is 0. We can say near the surface, the gravitational potential energy has to be negative. The potential energy near the surface has to be negative. Why? Because only if the potential energy near the surface is negative, will it increase to a potential energy of 0 at infinity. At infinity, it will increase to 0. That means when it has a potential energy of 0, it is outside the gravitational field of Earth. That means it is not under the influence of the gravitational force of Earth, right? The other way to think about this is as you move from infinity to closer to Earth, it loses its energy. Why? Because you're not doing work on the object to bring the object near the Earth's surface. The Earth is doing the work. The Earth is pulling the object near the surface. So you don't have to do anything. Therefore, the object will lose its energy from 0 to a negative value. So now, again, from near the surface, if you want to push it away, you will provide energy and increase it to 0. And from infinity, if it comes closer to the surface, that means it's losing its energy. So from 0, it goes to a highly negative value near the surface. Therefore, the first thing we learned, and first thing we have understood over here is at infinity, the gravitational potential energy is 0. Near the surface, the gravitational potential energy is negative. And since it is attractive force, that means in case of attractive forces, the gravitational potential energy is always going to be negative. Because bringing an object from infinity to a point near the surface, you don't need to do any work. The work is done by gravitational force, since it is attractive force. So you don't need to work against the force to bring it closer to the surface. However, when you take it away, move it away, you need to provide or transfer energy, in which case positive work is done. And bringing it from infinity to near the surface, negative work is done, because the work done is by the gravity of the mass. Therefore, the gravitational potential energy is always what? Negative, right? So that is the main purpose of this whole explanation, that near the surface, gravitational potential energy is negative. And always the gravitational potential energy is negative. Great. So now, how can we define gravitational potential energy? The exact definition is going to be, it is the work done in bringing an object or a mass from infinity to a defined point. So let's say the amount of potential energy that object A is going to have is the amount of work done that Earth did in bringing this object A from infinity to this defined point. That is how gravitational potential energy is defined. Therefore, near the surface, the gravitational potential energy will be highly negative, because bringing it from infinity to this point near the surface, a lot of work was done. Because near the surface, remember, there is higher amount of force. Therefore, greater work was also done, right? So as you move closer to the Earth's surface, force increases, which is also why amount of work done increases. But remember, potential energy is negative. Therefore, near the surface, a highly negative value of the object's potential. Therefore, again, the definition of gravitational potential energy is going to be the work done in bringing a mass from infinity to a defined point near the mass. From infinity to a point. Any defined point, anywhere. That is going to be your work done, and that is going to be your potential energy, right? So this is the definition. And the formula for gravitational potential energy is actually Gmm by R. Now, you may be confused by the formula of force and formula of gravitational potential energy. To make it clear to you, an easy way to remember this is Fg, force is Gmm by R squared. So the difference between both is, in case of force, the radius, the distance has a power of 2. In case of potential energy, the radius does not have any power. Therefore, Gmm divided by R, and there is a negative sign in front. Why? Because negative work is always done in bringing it from infinity to near the surface. Therefore, this is your formula for gravitational potential energy. You don't need to know how the formula is derived. However, if you are interested into knowing how GPE, gravitational potential energy of an object, the formula is derived, I will show you over here. So, from the last video, you know the graph of gravitational field strength. Now, I had also mentioned that the same shape of the graph is going to be for the force versus distance graph. It's going to be the same shape. So if we take that into account, remember near the surface, radius of Earth. So if this is the center of Earth, this is your Earth, this is the surface, this is a defined point R at which we want to find the gravitational potential energy at, and this is infinity. So remember the formula of gravitational potential energy, the amount of work done in bringing an object from infinity to a defined point, let's say R. So what is the gravitational potential energy of the object at this defined point R near Earth, here the mass, right? So remember the formula for work done, force into distance. So what you have over here is force on the y-axis and distance on the x-axis. So how will you find out the work done? You integrate. You find the area under the curve between R and infinity. That's how you're going to find the formula for gravitational potential energy. Therefore, from infinity to R, let's integrate. So you know the formula for force, Fg, and you're taking the upper bound as R, lower bound as infinity, because you're going from infinity to R, right? Great. So you're integrating with respect to R, because it is a function of R, gmm by R square, right? And this shape of the curve again is due to this proportionality of 1 by R square. Okay, so now to find the gravitational potential energy, if I integrate both, what you're going to have is this. So integration of Fg from infinity to R is going to give you the gravitational potential energy. Mind you, this is actually the sign for gravitational potential energy. This is how you denote gravitational potential energy, right? So for gravitational potential energy, integrate gmm by R square, the force from infinity to R. Take the constants out of the integral sign because constants don't affect your integration. And what you can do now is integrate. How will you integrate 1 by R square? Very simple. It's going to be 1 by R to the power minus 2 plus 1 divided by minus 2 plus 1. It's going to be R to the power minus 1 divided by minus 1, which is going to be minus 1 by R. So this is your integration. Minus 1 by R. Does this match? Yes, it does. Minus 1 by R is your integration. Now you have to input the bounds, upper and lower bounds, right? So once you plug in the upper and lower bounds, it's going to be 1 by R, the defined point, minus 1 by infinity, right? This is going to be your value expression. So 1 by infinity is infinitely small, therefore we can write it as 0. So what you have over here is minus gmm by R. So this is how you get the formula for gravitational potential energy. This is the work done bringing the object from infinity to a defined point R, right? For you. Right. So this is your formula for gravitational potential energy. Okay, so in this part, we're going to see the difference between the previous and the derived gravitational potential energy formula. So I've already mentioned this towards the beginning of the video, that in case of mgh, that is the formula we used to use previously, the gravitation, the g value, the value of gravity, was actually a constant. That is, near the surface of Earth, the value of gravity is the same. Granted, the change in altitude is very small, right? In that case, this formula is, it makes sense because gravity stays constant. So change in height is going to give you the change in potential energy of the object. Now, mind you, this formula is accurate in terms of giving you the change in gravitational potential energy, which is the purpose of this formula, to find the change in gravitational potential energy. Now, what the formula that we have is the net gravitational potential energy of any object, that is bringing it from infinity to a defined point. At that point, what is its gravitational potential energy, right? Now, this equation is also derived from this complicated equation. How was it derived? Let's see. So for the change in gravitational potential energy, what does it mean? It means it goes from, let's say, near the surface of Earth to a position that is away from the Earth. So let's say it was initially at a distance 1 meter away from surface, and then it went 3 meters away from the surface. In those examples, notice it is moving away. Therefore, you're giving or putting in work into the object. You're transferring your energy into the object. Therefore, what we will do is find the gravitational potential energy at the final position, that is moving away from Earth, and the initial gravitational potential energy, right? So final minus initial gravitational potential energy is going to give you the del U, or change in gravitational potential energy. And we're going to see how this formula is derived, or this approximation is derived, right? So finding that out over here, the final gravitational potential energy is going to be minus G, mass of Earth, times mass of the object, divided by radius of Earth, that is up till the surface, plus the height that you lifted the object by, that is h. Meaning this height, change in height, is actually quite small compared to the radius of Earth, because we are considering, in this formula, we're considering the G to be a constant. Therefore, taking that into account, let's continue. That is final minus initial. So the initial will also have another minus sign, GMM by R, right? Now, as you open the brackets, GMM, by the way, initial means near the surface of Earth. So on the surface, the distance from the center is R, the radius. So R plus H plus GMM by R. Now, taking the constants out of the equations, therefore minus 1 by R plus H plus 1 by R. Great. So now, notice, if I do LCM over here, what's going to happen is we're going to have R times R plus H, and then we're going to have minus R plus H. Fair enough. So what we're going to be left with is this R and this R is going to be cancelled off, and we'll be left with H divided by R times R plus H, right? So now we can consider, remember, we consider the height to be small compared to the radius of Earth, right? Why is that? Because we are considering the gravity to be a constant. In which case, we can say R plus H is actually similar or approximately the same as the radius of Earth. Because let's say if you have a distance of 3 into 10 to the power of 6 plus 3 meters, is the 3 meters going to affect your overall distance? No, it's not going to. It's not going to affect your gravitation, which is why we can say R plus H is R. So we can say GMM divided by H by R square. GMM H by R square. Now remember the formula for gravitational field strength, right? The formula for gravitational field strength was Gm by R square. So take that away, and you're going to be left with G times mh. The gravity, not the gravitational constant, I mean gravitational field strength. Gravitational field strength times mass of the object times the height, the change in height. The change in height. So this is actually going to give you the change in gravitational potential energy. Therefore, this derivation is how we get the formula for mgh, right? Fair enough. So in this video, that is all I'm going to talk about. So we learned about the formula for gravitational potential energy, and we learned about how mgh was derived, and what it means to have a negative gravitational potential energy. So I'm going to keep it there. And another thing I'll add though is, notice this is how we derived, this derivation is how we derived the formula for GMH, that is, mgh, better known as mgh. So this is how we found out the change in gravitational potential energy for distances near the surface, right? Now, in the case that you are really far away and you cannot make this approximation that r plus h is actually equal to r, in those cases, what you're going to do is find the gravitational potential energy of the final position, that is, be it near the Earth's surface, be it away from the Earth's surface, does not matter. Find the final position. So if this is Earth and this is point B and point A, if you're going from point B to point A, find the gravitational potential energy at point A minus the gravitational potential energy at point B. So what this is going to give you is the net change in gravitational potential energy, and it is supposed to be positive because you're moving away, right? You're putting or transferring in energy to the object. Therefore, in that case, the change in gravitational potential energy will be positive. And in that case, you're going to use the formula minus Gm m by r minus Gm m by r2 r1, right? This is how you will find out the change in gravitational potential energy if the change in change in separation is really large, right? In those cases, use this formula. And I'm going to again talk about this in the video for gravitational potential, right? So see you in the next video.